In this video, we'll look at how to find the period of any system undergoing simple harmonic motion. So we're going to start with the most simple system which undergoes simple harmonic motion, namely a block with mass m connected to a spring with spring constant k, and specifically a linear spring where F equals negative kx. And with that, we want to recall a fact which you may have seen, which is that linear restoring forces lead to simple harmonic motion. We'll build on this as we go along. Linear because it is directly proportional to displacement, restoring because it pulls us back towards x equals 0. We also know that if an object is undergoing simple harmonic motion, its position can be described as x of t equals a cosine omega t plus phi. And so with our goal in this video being to find the period of our system, note that our goal is to find omega, because as we know, t is equal to 2 pi over omega. So with our goal established, let's think about how we could possibly solve for omega. I'm going to propose that we do this by trying to solve instead for x of t as our starting point. Okay, where to start with that? Well, a good place to start would probably be F equals ma. And in fact, this will be our starting point. F equals ma, or torque equals I alpha will be our starting point for analyzing any system undergoing simple harmonic motion. In this case, we have a linearly displaced system, so we'll focus on F equals ma. The only force acting on our block is our linear restoring force, negative kx. And so I can say negative kx equals ma. Now, of course, we can see that our acceleration is not constant. So in reality, what we have here is negative kx of t equals ma of t, which means we do not yet have a solution for x as a function of time. But of course, we can think about the relationship between a of t and x of t, and we'll remember that a is x double prime of t, second derivative of position with respect to time. And I'm going to drop my subscripts of t, or my parentheses of t, but let's rewrite this equation. So what we have is mx double prime is equal to negative kx, which we can rewrite as mx double prime plus kx equals 0. Finally, I'm going to rewrite this as x double prime plus k over mx equals 0. And this will now be a foundational equation that we'll keep referring to throughout this video. So in order to really see what this equation is telling us, I'd like us to consider a simpler case. Let's imagine, or not imagine, let's take a case where k equals m, such that our equation now becomes x double prime plus x equals 0. Or alternatively, x double prime equals negative x. What is this equation telling us? It's telling us there is some function, x of t, such that when we differentiate twice, we get back the same function with a negative sign. Well, what function does that? I encourage you to pause your video and try thinking through some basic functions. This is a function you well know that has this behavior. You've paused the video. Hopefully you've come up with one or two functions which have this behavior, namely cosine of t or sine of t. If I take the first derivative of cosine t, I go to negative sine. And then if I take the second derivative, I get back negative cosine of t, which is exactly the negative of my original function. And we have the exact same result for sine of t. Moreover, you should hopefully see that this is true not only for cosine of t, but a cosine of t plus phi. The amplitude and the phase constant make no difference. It satisfies the equation. X double prime is equal to negative x. Now, with that in mind, let's consider the general case. Right now, we considered a special case where k over m was 1. What if k over m is not 1? This is where we'll be doing the following. We are going to propose what we call an ansatz solution. In other words, we're going to say, I think x of t should still be trigonometric because it was trigonometric in this particular case. So I'm going to propose that x of t is equal to a cosine omega t plus phi. So the change we've made here is we've said, well, k over m isn't 1. I'm not sure what omega should be. And where do we go from here? Well, I'm going to start by first computing x prime. X prime will be negative omega a sine omega t plus phi. And then x double prime will be equal to negative omega squared a cosine omega t plus phi. And now I'll go ahead and plug that into our differential equation right here. So x double prime, we have negative omega squared a cos omega t plus phi plus k over m times my original x of t, which is a cos omega t plus phi. Set all of that equal to 0 because that is what our differential equation says. Now, what would make this equation be true for all time? I'm going to combine my like terms so that we have negative omega squared plus k over m all times a cosine omega t plus phi equals 0. And what we'll note is that for this to be true for all time, negative omega squared plus k over m must equal 0. And this tells us that therefore omega equals square root k over m. This hopefully is a familiar equation, and we therefore can conclude that the period of a spring block system is equal to 2 pi square root m over k. So with that, we found the period of a spring block system. In the next video, we'll see how we can generalize this result to find the period of more complicated systems, beginning with the simple pendulum and then moving on to physical pendulums.